Hi there! This video series is to display my problem-solving and learning abilities. I hope to show that I can solve any programming problem, regardless of whether I already have expertise in the language at hand. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. For now, I am learning Python. I have no professional experience or formal training in the language, and have only been learning it since mid-January. While I'm picking up fairly quickly, I cannot claim any real expertise. Today, I am going to show my approach to solving the fifth Project Euler problem. Full disclosure, as you can see, I have already solved this one as well, but I'll be starting fresh and talking through my thought process. Also, this is the last one that I have previously solved, so hopefully the series gets more interesting here on out. I will link to both Project Euler and my repository in the description. Let's dive in. Problem number 5 is the smallest multiple, and it says this number is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest possible positive number that is evenly divisible by all of the numbers from 1 to 20. Let's go ahead and take this problem statement and move it over to our Visual Studio Code. And again, as the last couple of times, since I do have the answer, I'm going to copy that over so I can most easily verify. So for this one, let's actually think through the problem manually, and then think about how to automate it. So all of the smallest possible number evenly divisible by all of the numbers from 1 to 20. So obviously, one way to do this, the very simple and actually inaccurate way, would be to just multiply all of those numbers together. But let's think about it in terms of prime factors. So 20 is 2 times 2 times 5. 19 is actually a prime number. 18 is 2 times 3 times 3. And this is 2. Oh goodness. It's a good thing typing is not the most important skill for a programmer. 15 is 3 times 5. And 13 is prime. Took me a second. So I'm mostly doing it this way as just sort of a making sure we thoroughly understand exactly the problem. And I think it's already showing that, like, if we think about it in terms of our prime factors, we should be able to automate this without having to go through tons and tons of numbers. And then, of course, 2 equals 2. And we're not even going to worry about 1 because, come on. Every number is divisible by 1. So, we can either think of this from 20 down or 2 up to 20. I think for purposes of making it programmatic, it's probably more sensible to start with the number 2. So let's sort of write out a strategy here. So in our range 2 to 20 inclusive, so for, let's see, n in range 221, and we want to, I think, do what is called a counting sort, where we look for the prime numbers and count how many of them there are. I think that in Python, from the little I know, a dictionary is probably the most effective way to do this. A dictionary is a lot like an object in JavaScript or Java. And it's a lot like a map in Java as well. But I think that is what probably makes the most sense. So we want to find prime factors, check dictionary for prime factors, and then if of a prime factor is less than kernum of that, increase dict. So let's see. We want our little object here. Let's call it, let's say num primes, and that is going to be an empty dictionary for the number 2. And actually, we worked with prime numbers very recently on problem 4, so let's go ahead and open that. Okay, I was incorrect. I think it was problem 3. So first, we want to grab these 2 methods. We're just going to steal them. It's our own work anyway, and that's allowed. So we have our isFactor and isPrime. And we had our little primes array to use as just a cache, a very, very simple cache. So we have to copy that over as well. So find prime factors is going to be, let's say for I in range 2 n plus 1, just to make sure we're also going to get 2. If I, let's say if is factor I n and is prime, this is very similar to what we did in problem 3, where we checked whether for prime factors. Let's do count equals okay, so we actually need to have an inside dictionary as well. So let's say kernum primes. And let's see, so if it is a factor and it is prime, then we actually want to take in and decrease it. So let's see. so we want to have curnum primes. And I think that if I do this, it will just automatically create the key. Maybe not, but let's give it a shot. And if we have errors, we have errors and we fix them. So curnum primes equals 1, because we found that it is a prime factor. And then while and this is going to be n equals n divided by I. So what that'll do is basically, like for the number 4, for instance, we're going to come in, number 4, we get to the number 2, we say, is this a factor? And is it prime? Yes, because it's the number 2. So we have 1, 2 in our dictionary, or we add 1. And then we take that 4, we divide it by 2. Actually, let's say curnum primes 1I equals 0 so that we can do this. And again, I'm not 100% certain that this will work in Python. I haven't worked with dictionaries very much, but let's see how well that goes. Then what I'm actually going to do is just print our curnum primes here so that we can see how far we're getting. So Python problem 5. Okay. Well, that makes sense because I forgot to do the bracket I. Okay, so for 2 we get 1, 3 we get 1, 5 1, 7 1, 11 1, 13 1, and 19 1. Interesting. So it's only getting the prime numbers themselves. It looks like. So, what's happening with number 4? Let's actually go ahead and put this inside the while loop, just to see. Okay, so something's clearly not going the way that I expected to. Ah, it's because this curnum... Or, well, no, it's probably not because this resets for every number. But, let's see. We want our num primes dictionary, though, to do num primes I equals... which shows that this doesn't actually need to be a dictionary. It can be just an integer. And if I remember correctly, I can do this in Python, so let's go ahead and do that, make our code a little bit more readable. Okay, so now... Obviously, this is not going to end up working, but let's just kind of see what it does. Okay. So, again, it's never getting up above the number 1. So it's going into the loop, but only for the prime. Let's add some more prints so that we can kind of see closer what's going on. Let's see. Okay, that's got a lot more numbers in it. Or a lot more output, I should say. Scroll up to number 4, which is the most interesting. Checking I. Oh. So that's intriguing. Because the number 2 is not showing up. So let's see. N3, oh, N3 is a prime factor. Of course the number 2 wouldn't show up for N3. So N4, so 4 is not showing up as a prime factor, which is interesting. I wonder if this was broken previously. In our other problem, it looks like the number 2 isn't being added somehow. Let's add a print here. I find that prints, just printing out, is the easiest way to figure out what's going on with my program. Okay, so N2, checking I of 2, 2 is prime factor. Then we have this one, which is our kernel primes. N3, checking I, checking 2, N4, checking I2. Oh, I see what's going on here. So this is written so that, like, it's expecting on a higher number to always so we have to do this little check to say, hey, if the possible prime is in I, then yeah, that's... Actually, let's do it like this. If possible prime in primes, that's not what I wanted. Then return true. Otherwise, check whether a prime has a factor of the number. Okay. So that should get us working closer to how we want to be working. Let's look at number 4 again. Okay. Okay, so we're getting there. we're getting a lot closer. Let's stop printing out our primes, and let's stop printing out this and this. Let's leave this for right this second. And this we have to do a little bit of a check here. If num primes I is less than cur num primes, then we want to set it. And then for key n num primes, count equals num primes key. So basically, let's go through this dictionary that we made, and for everything in the dictionary, we just multiply it that many times. So we actually need our sum equals 0, 1. Or let's instead of calling this num, let's call it answer. And maybe not have a bunch of white space on the line, preferably. For j in range 0 count. Little bitty trick there to have it go the number of counts exactly count times without having to do a +1. And we'll just do answer equals answer times key. And then we're going to print answer. And if I am correct in how this works, then it should print this number here. Otherwise, having these print statements should help us figure out exactly where the problem is. So let's see. Cool. Ooh. Okay, so this is actually a thing that I just learned from execute program today. We can call get I and let's call it a 0 as the default value. So basically we are getting the key or the number 0, so we can always have, we can avoid this key error. So let's try it again. Here's our big number, 232,792,560. So there we did it. And is this super efficient for, obviously, for numbers up to 20? Yes. If we made this number much larger, would it still be efficient? No, I don't believe it would, because we're effectively doing an n squared, an O of n squared here, which, again, it's fine. We see that it works very quickly in Python, almost instantly, clearly not up to a minute. If this number, however, were like, say, 50, let's see, that would probably take quite a bit longer. Let's see. Okay, never mind. It does not take very much longer in Python. Python is cheating. But in any case, this does work. It might not, by the count of O of n, be the most efficient possible method, but it's obviously quite functional. Always end with a new line there. So, yep, that'll be it for today. And again, next time will be a little bit more interesting, as I have not faced that problem before, and you might get to see me struggle more. Alright, see you then.